Welcome to Mrs. Z's Chemistry. In this video, we'll do some more practice problems with gas laws. So let's look at this one. If you heat up a balloon in the oven that initially had a volume of 0.30 liters and a temp of 74 degrees Fahrenheit, what will the volume of the balloon be after it heats up to 500 degrees Fahrenheit? To figure out which equation we need to use, we need to ask ourselves, are we given final and initial values? The answer for this problem is yes, because we have an initial volume, we have an initial temperature, and then we are given a second temperature or a final temperature and asked for what will the volume be. So that's the second volume. So let's look at the equation box on the periodic table for gas laws. All we have in this problem is volume and temperature. So that means we need to use Charles' law, where we have volume and temperature, a changing volume and a changing temperature. The next thing we need to remember is that the temperature must always be in Kelvin for these problems. So first, let's convert each Fahrenheit temperature into Kelvin. Then we'll use Charles' law to solve the final volume. Pause to work this video out before seeing the final answer. So here's the answer. The reason that we must use Kelvin is because you can see that the second value for temperature in Kelvin here is not quite double of the first value for temperature. And if you were to compare these temperatures in Fahrenheit, the second one here is almost 7 times greater than the first one. So you can see that the volumes would not come out correctly if you were to use the Fahrenheit values versus the Kelvin. Even though you might think the Fahrenheit units would cancel, the concept of this law comes from using Kelvin, which is the kinetic energy of the molecules. Pause this video to read this problem and figure out which equation to use and then solve. So here's the answer. First, we need to use the ideal gas law, or PV-NRT, PV is equal to nRT, rearrange to solve for moles, as you can see here. Then, plug in the pressure, the volume in the numerator, and the R value and the T in the denominator. When we calculate this, we have 1.259 moles of methane, or CH4. However, the problem is asking for how many grams of methane do you have. So then just convert the moles to grams using molar mass of CH4. This problem is asking for molar mass, which has units of grams per mole. So let's go to the periodic table and find this equation. To solve for molar mass, given pressure and volume and temperature, we can use this equation where G is equal to the grams given in the sample of the problem. See if you can solve this problem. If you plug in 50 grams for the G in the equation, and then you have the R value, and then the temperature, and then pressure and volume in the denominator. So let's look at the units here. We can see that the liters are canceling, the atmospheres are canceling, the Kelvin is canceling, and you're left with grams per mole, which is exactly the units we need for molar mass. 154 is rounded to 3 significant figures. Now let's try this problem where we calculate for the density of a substance. Going to the periodic table, you can see that we have this equation where the MM comes from this MM for molar mass. So that's molar mass of the substance times the pressure divided by R divided by temperature. Remember, this is your R value. It's a constant. So go ahead and see if you can solve this problem. Here we have the molar mass of carbon dioxide. Carbon dioxide here is CO2. So add up 1 carbon and 2 oxygens from the periodic table to get the molar mass of carbon dioxide. And then you have the pressure in the numerator as well. And then your R and your T value. So let's look at the units here. We're going to cancel moles. The ATM gets canceled. The Kelvin is canceled. And we're left with grams in the numerator and liters in the denominator, which is mass over volume, which is great for density. The molar volume of any gas at standard temperature and pressure is 22.4 liters. This means that when we have 273 Kelvin, which is standard temperature, and 1 atmospheric pressure, standard pressure, then 1 mole of any gas will take up the space of 22.4 liters. Remember that this is only at STP. If your temperature is different or pressure is different, that 1 mole of gas will take up a different amount of volume.